Alright guys, welcome back for another video, this one on section 4.5. We're going to be discussing linear independence and dependence of vectors. Today, not a lot of prerequisites here. You need to know about spanning sets and how those relate to vector spaces and linear combinations, okay, which all of those things you can find in the lecture for section 4.4 if those things don't ring a bell. So the first things first. Linear dependence and linear independence are mutually exclusive. We define them in a complementary sense in that things that are not dependent are independent and things that are not independent are dependent. And so the reason I'm bringing that up is we can go about this by either defining what dependent means and then things that are not that are independent, or the other way. And your book provides one definition for each, but we're going to operate using the definition for independence and then say that things that are not independent are then dependent. Okay? So let me give you a quick definition of linear independence. So, a set of vectors, let's say v1, v2, all the way to vn, which are members of some vector space v, I don't know, doesn't really matter, are considered to be linearly independent if the only, this is the very, I'm going to put this in another color because this is the most important word in this entire definition. If the only set of constants C1, C2, all the way to Cn, such that C1 times V1 plus C2 times V2 plus Cn times Vn is equal to 0, the zero vector, are that every C is equal to 0. Okay, so let's just take a look at this equation for a moment, right? This is a linear combination of all of these vectors. Yes, remember that from section 4.4. Some constant times vector 1 plus some constant times vector 2, etc., etc., etc. Okay? Now, I know that for any collection of vectors v1 through n, doesn't matter what the vectors are, I know there's at least one set of constants that will make this equation true. I can just make every constant 0, right? 0 times vector 1 plus 0 times vector 2 all the way plus 0 times vector n, that is going to be the 0 vector. 100% of the time, all the time. But maybe that's the only solution, right? Maybe every other combination of constants you could put in here doesn't give you the 0 vector. That is linear independence. Okay, that is linear independence. The opposite would be something like would be what we call linear dependence. I'm going to give you some examples in a second. Okay, so we're going to operate under this definition. Now, a lot of the time when we're looking to determine whether or not a collection of vectors is linearly independent or dependent, we're not going to go by this definition because it's long and wordy and more difficult to use than some shortcuts that we're going to come up with for other types of for other collections of vectors. And let's look at a couple examples so we can maybe round out our understanding of what these things mean. So let's take a look at, for example, let's take this canonical basis for R2. Oh, that's supposed to be a 1. Okay. This is linearly independent. Why? Well, let's go to the actual definition. To claim that it's linearly independent is to claim that C1 times my first vector plus C2 times my second vector equals the 0 vector has exactly one solution. C1 and C2 both have to be 0. Is that true? Well, we can find out. Yeah? Multiply these two things together. I get C1 comma 0 plus 0 comma C2. Let me add these two, add them component-wise. You get C1 comma C2, and I have C1 comma C2 is equal to the 0 vector. So the first component reads C1 equals 0, and the second component reads C2 equals 0. This is somewhat trivial, yes? But again, notice that the only possible solution, C1 and C2 are both 0. This is independence. As opposed to, okay, let me give you an example of dependence. Okay. Let's say I have the following collection of vectors, F1, F2, and F3, and these are members of P2. F1 is equal to 1. F2 is equal to 3 plus 2x squared. And F3 is equal to negative 5x squared. Okay. So again, these are three vectors. These are all members of P2. Remember what P2 is? It's the collection of all polynomials with degree at most 2. And I claim that this collection is dependent. So again, what am I claiming? I'm claiming that for the equation, C1 times F1 plus C2 times F2 plus C3 times F3, when this is equal to the 0 vector, and again for P2 that's 0 plus 0x plus 0x squared, I'm claiming this has more than just the trivial solution, all of my constants are 0. That does work, right? All your constants 0 does work, but I claim there's other solutions. Well, let's see if we can't find some. Okay, plugging in F1, F2, and F3 here, I get C1 times 1 plus C2 times 3 plus 2x squared plus C3 times negative 5x squared. Okay, I'll leave the right-hand side because it's not going to change. Let me distribute. I got C1 plus 3C2 plus 2C2x squared plus negative 5C3x squared. And if I group together my terms, my constant terms and my quadratic terms, this gives me C1 plus 3C2. Oh, left off the C2. Here we go. 3C2 plus 2C2 minus 5C3 x squared. That's equal to, again, my 0 vector, 0 plus 0x plus 0x squared. Okay? And again, we can look at this in terms of components. I have a constant component and I have a quadratic component. The constant component tells me that C1 plus 3C2 must be 0 because the constant on the left must be equal to the constant on the right. My quadratic coefficient here is 2C2 minus 5C3, and that must be equal to 0 because my quadratic coefficient on the left must be the same as my quadratic coefficient on the right. Now this gives me C1 is equal to negative 3C2, and C3 is equal to 2/5 C2. That's the best I can do as far as solving is concerned. But what does this mean? This means that any collection of constants which satisfy these two conditions will in fact cause this equation to be true, be consistent. Let me pick one, right? I don't have to choose one, but let me choose one. If, hypothetically speaking, I'm going to choose C2 to be 5, okay? I'm going to let C2 be 5. And let's look at this. This says C1 is equal to negative 3C2. Well, that's fine. That would make C1 equal to negative 15. And this last one says C3 is equal to 2/5 times C2. So that would make C3 equal to 2. Okay? And I claim if you plug these things into this equation, you do in fact get 0. Okay? Let's see if it works. I'll leave this down here for a little bit longer. Okay, let's see. C1, negative 15. So this is negative 15 times F1, that's 1, plus C2, that's 5, times F2, that's 3 plus 2x squared, plus C3, that's 2, times negative 5x squared. Let's see what I get. Okay, expanding everything, I get negative 15 plus 15 plus 10x squared minus 10x squared. Sure enough, that is 0, right? 0 plus 0x plus 0x squared. This works, right? I have a solution here that does not involve all my coefficients being 0. This is called a dependency relation, okay? So this is called a dependency relation. Now, if I want to demonstrate that a collection of vectors is linearly dependent, this is all I really need, right? I just need some solution for this equation here that's not all zeros, right? So this would have worked. If you would have just said C1 negative 15, C2 5, C3 is equal to 2, that is enough proof to demonstrate dependence, okay? Because, of course, it follows this rule. Now, it's better to go ahead and find the rule, right? Because for completionist's sake, we want to make sure we find all of the possible dependency relations, okay? But again, what we've discovered is that this is a linearly dependent collection of vectors. Now, I've given you definitions. And I've shown you a couple of examples. I'm going to get to some more specific versions, dependency in Rn and dependency among functions here in a bit. But I want to give you sort of a short explanation for what this means in the context of what we're doing. Remember that we're going to be using these vectors to span other spaces, right? Okay, let's take P2 for example. Okay, on the one hand, you can write a definition for P2. It is infinitely large, so you can't enumerate all of the things inside of it, okay? But I could describe it, right? Another way to write this down is as the span of several other objects. And in the lecture for 4.4, we made mention that we can say that the span of the following vectors, 1, x, and x squared, the span of that is P2, right? If I take some linear combination of these three, everything in P2 can be written that way, right? And that makes sense. We've done this lots whenever we're talking about quadratics in grade school. Every quadratic is some constant times x squared plus some constant times x plus another constant, ax squared plus bx plus c. Okay? But let's say I give you other vectors in P2, and I ask you, Okay, maybe they don't span P2, but are they linearly independent? So let's talk about, let's say, this collection of vectors. Maybe 1 and x. Now clearly this doesn't span all of P2 because you can't make quadratics from just 1 and x, at least not with scalar multiplication and vector addition. But couldn't I make anything of the form, so the span of this, isn't this every polynomial of the form ax plus b? This is just all linear polynomials. Okay? Well, in that sense, is this a linearly independent or dependent set? Well, here's another way to think about it. What if you take away one of these vectors, right? Now there's two ways I could do that. I could take away a vector by turning this into this set by taking the x out. Or I could take one away by taking the 1 out. My question is, if you take one out, does the span change? Right? Well, let's see. Let's write what the span of these two things are. Well, the span of x is just, well, that's just all the polynomials that look like a times x, right? Okay, well that's clearly different, yeah? Because I know, for instance, 2x plus 1 is in this span, but it's not in this one. I can't make 2x plus 1 just by multiplying x times a constant. I can make 2x, but I can't make the plus 1. And the same is true for the span if I take the x out, just the span of 1. These are, again, all the polynomials of the form b, some number, right? Well, sure, but again, like I said, 2x plus 1 is in this span, but it's not in this one, it's not in this one either, because I don't have any x's to work with. So in this sense, both the 1 and the x provided useful information for creating this span. Okay? This is a sort of intuitive definition for what linear independence means. A set is linearly independent if every single item in that set is useful for the creation of the span. If taking any one of them out would cause a reduction in what you can span with the new set. Okay? So, for example, these two vectors these are also vectors in P2, right? So these are also vectors in P2. And together, what do they span? Well, it would be a mistake to assume that because you have a linear term and a quadratic term present, that you could span, let's say, all polynomials that look like ax squared plus bx. Okay? This is just not true. Okay, in this case. Okay, so this is not true. It would be a mistake to assume that. Let's see what they do span. Well, let's look at them under that sort of guise of independence and dependence. What if I took a constant, multiplied it times my first vector, and add to that a constant times my second vector? Now, again, the goal here is to create the 0 vector here. And let's see how that might be done. Again, grouping all of my terms together after I distribute, I'm going to shortcut it a little bit this time. This is going to be 2c1 minus 4c2 times x plus negative 5c1 plus 10c2 x squared. Again, the coefficients on the left have to match the coefficients on the right. This gives me the two equations. 2c1 minus 4c2 is equal to 0, and negative 5c1 plus 10c2 also equal to 0. Let's rearrange these into a slightly more appropriate form. I get c1 is equal to 2c2, of course moving the c2 term and dividing by 2. Again, solving this equation for c1, I get c1 is equal to, well, I also get 2c2. And yes, if they're both 0, that's a solution here. We know that already. The question is there a solution not to that? And sure. My work here says that if I pick any constants that obey these relations, that's going to work. Well, yeah, but all it requires is that C1 is double C2. All right, well, pick C2 is equal to 1 and C1 is equal to 2. That does it, right? Now, maybe you guys saw that from the start. You'll notice something very curious here, and that's that my second vector here is a scalar multiple of my first. If I take this vector and multiply it by negative 2, then of course I get the second vector. This creates dependence in this case. If you ever have two vectors and one of them, and they are what we call proportional, so one of them is a scalar multiple of the other, that will always create dependence, but that's not the only way to do it, right? It is possible to have, let's say, a collection of 3 vectors, and those vectors, none of them, no two of them are scalar multiples of one another, but they're still dependent. Okay? So what are we talking about here? Well, what we're saying is, we're saying that this is dependent because this vector was already in the span of this one, right? If I just were to look at the span of 2x minus 5x squared, isn't this span just all polynomials which are equal to some constant times 2x minus 5x squared? That's what span means, right? But if this is true, then again, if a is any possible real number, then hypothetically a could be 2. Okay? A could be negative 2. And if a is negative 2, then this is... So we notice that if a equals negative 2, then we see that negative 2 times 2x minus 5x squared, that is in the span, right? That's in the span. But that is negative 4x plus 10x squared. This was already in the span. So if, again, hypothetically, if I just take this vector out, right? Let's say I just you don't even need this. I don't lose anything. The span is the same if I take that out. This vector was not important. It wasn't useful. It didn't provide information. That's what dependence means. A set is linearly dependent if at least one of the pieces of information in there, at least one of the vectors, is superfluous. It's extra, right? if it's not needed for the creation, the full creation of that span. Now, again, we could go by the definition. You can always go by the basic definition. We can always write out that equation. We can always solve for those relations and see what we get, and then figure out whether or not all those constants have to be 0 or whether or not they don't. Yeah, but that's kind of a pain. And so we want maybe a slightly more efficient way to do this if we're talking about maybe, if we're being a little bit more narrow with our choice of vector spaces. And so let's talk about Rn, right? Let's talk about just real valued vectors, okay, in Rn. And let's maybe talk about, I'll get an example up here. Let's do maybe 1, 2, and 3, 4, 5, 6, 7, 8, and 9. Very lazy, I know. Now, I know that all of these vectors live where? Well, these vectors live in R3, right? Again, look at the vector itself, this vector, I've got 1, 2, 3 components, right? So it's got to live in R3. Okay, fine. Is this collection of vectors linearly independent or dependent? Okay. I'm going to write this out, but in the end, we're going to kind of draw all these things together, and we're going to see if we can't shortcut this whole process a bit for real valued vectors. Asking about linear independence versus dependence is again asking the same question. What if you took the equation C1 times my first vector plus C2 times my second vector plus C3 times my third vector is equal to my 0 vector? What kind of solutions does this have? I know it's got 1, 0, 0, and 0, but does it have more? Well, let's see. Distributing in each of these and then adding the vectors together, I get the following. I get C1 plus 4C2 plus 7C3. That's my first component. Second component, 2C1 plus 5C2 plus 8C3, second component. And my third component is 3C1 plus 6C2 plus 9C3. That's got to equal my 0 vector, right? But again, the components don't interact with one another, so really this is 3 separate equations. This is C1 plus 4C2 plus 7C3 is equal to 0. Blah, blah, blah. Where's my second one? Here we go. 2C1 plus 5C2 plus 8C3 is equal to 0. Second component. Third component also has to be 0. 3C1 plus 6C2 plus 9C3 also must be 0. Okay. Well, sure. But ignoring how we got here, isn't this just a linear system? We know how to solve linear systems, right? Yeah? I can make an augmented representative matrix, yeah? And then I can put it into a row echelon form. I can use what's called Gaussian elimination and back substitution. So let me go ahead and do that. I'm going to go ahead and solve this linear system. Okay? I need to do it in another color though. Here we go. So let me go ahead. I'm going to solve my system. Okay. So again, my representative matrix here. I've got 1, 4, 7, 0, 2, 5, 8, 0, 3, 6, 9, 0. Okay. Let's see if we can't get this into some sort of row echelon form so we can get the solving done. It's nice a bit to not have to pivot. It's got a 1 there already. Let me use this one to annihilate the two values below it. That's A12 negative 2 and A13 negative 3. Okay, first row doesn't change. That's 1, 4, 7, 0. All right, let's look at my next row. 1 times negative 2 plus 2 is 0. 4 times negative 2 is negative 8 plus 5 is negative 3. 7 times negative 2 is negative 14 plus 8 is negative 6. That's still 0. 1 times negative 3 plus 3 is 0. 4 times negative 3 is negative 12 plus 6 is negative 6. 7 times negative 3 is negative 21 plus 9 is negative 12. Okay. I can pivot here. Go ahead and multiply that second row by negative 1/3. That'll give me the 1 I need, and it's not going to make any fractions, so that's nice. Multiply row 2 by negative 1/3. Okay. Row 1 doesn't change. 1, 4, 7, 0. Row 2 becomes 0, 1, 2, 0. Row 3, still 0, negative 6, negative 12, 0. Clearly I can finish this off by doing A23, 6, and that gives me 1, 4, 7, 0, 0, 1, 2, 0, 0, 0, 0, 0. Okay, now I can back substitute, right? That second row is the equation C2 plus 2C3 equals 0, hence C2 equals negative 2C3. The first equation reads C1 plus 4C2 plus 7C3 equals 0. And again, solving for, I can replace C2 with negative 2C3, and then solving for C1, I get C1 is equal to negative 5C3. Oh, that's not right. It's negative 8, negative 1, positive C3. Positive 1C3. And if you see, I've got the same relations, well, similar relations at the end, right? Sure, letting them all equal 0. If I let C1 be 0, then C3 is 0, then C2, that's fine. But there are other solutions, yeah? If I let C3 be 1, then C1 is 1, and C2 is negative 2, and that would work, yeah? Now, this seems like a lot of work, and really we could have shortcut this process a whole lot, okay? As long as you give me real valued vectors, right? So again, just a string of numbers, right? Won't it always end up being some weird sum like this where I've got a giant vector, it's equal to 0 vector? At which point in time, again, it'll always turn into a system, which I can always put into a matrix, and then put into row echelon form, and then of course use that row echelon form to solve. Well, yeah, but look at my original vectors. My original vectors were here, here, and here. Those same vectors can be found here, here, and here. When you're looking at real valued vectors and you would like to identify dependence or independence, you can just load them into a matrix and put that matrix in row echelon form. Okay? Now, I'm going to erase this. I'm going to put some of this information back up here. Okay? Some of this information back up here. Here we go. So let's say we had done that. Let's say we saw the real valued vectors. We said, okay, what I'm going to do is I'm going to put these things into the columns of a matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And I undergo some elementary row operations. I'm not going to write them all out again. And I get 1, 4, 7, 0, 1, 2, 0, 0, 0. I know some of you right now are focusing on the fact that I did not recopy the solution column. But I don't need to because, again, it's all zeros. It's always all zeros. Okay? Now, what does this mean? If I take this and I convert it into some relations, which we did, we got C1 equals C3 and C2 equals negative 2C3. The only way I don't get a unique solution is if I have a row of all zeros, right? That comes from our invertible matrix theorem. Okay? It's equivalent to say that this, with a solution column of all zeros, remember that statement A times X equals 0? It's equivalent to say that that has only the trivial solution, all zeros. That's equivalent to saying the rank of this matrix is n, and we see that the rank is not n. N is 3. The rank is 2. The conclusion here, or what we can draw from this, is that rank has, again, an alternative meaning. We can think of rank as a quantification of how much information is in a collection of vectors. There are 3 vectors here, but the rank of this set, the rank of the matrix and the rank of the set then, is only 2. Notice that the rank of the set is less than the number of vectors. Okay? If the rank of the set V1 to Vn is less than n, then the set is linearly dependent. Okay? Dependent. Well, this is fantastic. This gives me a very quick and easy way to take a collection of real valued vectors and identify linear independence versus dependence. Okay? Take them, stick them in a matrix, put it in row echelon form. If you get a row of all zeros, then the rank will be less than the number of than the number of vectors. That's it. Must be linearly dependent. Now, notice something I said, connection to something I said earlier. I said if you have 2 vectors and they are scalar multiples of each other, so they're proportional, that's linear dependence. You will notice none of these vectors are a scalar multiple of the other one. Okay? And yet again, this is dependent. How? Well, this rank being 2 also tells me what type of space is being spanned. Now, I can't tell you exactly where the span of this is, but I can describe it. Okay? This span, since it has rank 2, this span is a 2-dimensional subspace of R3. Okay? I know it's a subspace of R3. We talked about that during the section on spanning sets. The span of every collection of vectors is a subspace. The question is which subspace, right? So I know it's a subspace, but I know very specifically it's 2-dimensional. And I know it's 2-dimensional because, again, the rank is 2. It's got 2 units worth of information in it, right? Dimensions worth of information. Well, then what does that mean? Well, it's a plane, right? Planes are two-dimensional. The span of these represent a single plane within R3. The reason they're dependent is that they're all located on the same plane, right? And I don't need 3 vectors to represent a plane. I only need 2. Clearly, at least one of them is superfluous. The next logical question some students ask is, well, which one is superfluous, right? Which one can I do without? And in this particular case, you can actually throw out any one of these and it would be fine. The span of these 3 is equivalent to the span of any 2 of them that you would possibly choose. Now that's not true in general, okay, but it is true in this particular case. Okay? Okay, so this is very nice for us. We'll talk about what we've talked about, what linear independence and what linear dependence are, how we can find those things, how we can find dependency relations. But then for a very special case for Rn, we have a much cleaner, quicker way of determining dependence and independence. Now, this is just going to be part 1 of these lectures on independence and dependence. I'm going to do another part where I talk about how we can maybe tie some of our other skills into this, namely determinants, and then how we can use that along with an interesting construction called a Wronskian to where we can determine linear independence or dependence between functions, because that's what we're really looking for, is to be able to classify those infinitely large solution spaces to our differential equations. And to do that, of course, I need to be able to identify which functions are linearly independent from one another. All right, guys, I'll see you next time.